the things that amateur astronomers like to talk about. He gave us a beautiful observing list of really cool things to look at. M51, here's from the Hubble Space Telescope, was number 85 on HARP's list. He gave us a challenging observing list of very difficult things to find, very small. He explained the redshift and what it meant in relation to the distance of things in the universe. He debunked the Big Bang. He was wrong, and he was most certainly peculiar. And you'll see especially what I mean about that peculiar part. But let's start off with the easy stuff. Back in the mid-20th century, he was just an up-and-coming young visionary. He was a star astronomer in the making. Halton Arp, he was often called Chip. He was born in 1927 in New York City and died in 2014 in Munich, Germany. It should be noted that his father was an artist, not Gene Arp, the famous Arp artist, but and Chip and his family moved around a lot. It appears the truant officer was not too diligent with his family. Chip's first day in school was in 5th grade, and the next year he skipped to 7th grade. But, you know, it was the recession, the depression thing going on, and the war, of course, and this and that, and the other thing. But although he was a late starter at this school thing, he was pretty good at it. After a brief stint in the Navy at the end of World War II, he got into Harvard. By the way, his faculty advisor at Harvard was Bart Bach, famous for collecting dark things. How's that for a little foreshadowing as to what's going to happen? In 1949, he graduated Harvard cum laude. He's careful to note in his autobiography. He then moved to the California Institute of Technology, where a few years later, he earned his PhD. Also cum laude, also duly noted in his autobiography. The freshly minted doctor in astronomy went through various short-term appointments and in 1957 hooked up with the biggest telescope in the world, the Palomar 200-incher. He worked on that perfect machine for the next 29 years. In that tenure at Palomar, he was recognized with the Helen B. Warner and the Newcomb Cleveland Awards. After all, he was up and coming, and he hobnobbed with the big names in the science. Now, there are a few things that you should probably pick up from this first slide, a little more spooky foreshadowing. One is, as he remarked in an oral history about not starting school until he was in 5th grade, was that it was obviously at a disadvantage in the sense that I had not developed my socialization skills. When I did go to school, you know, getting along with other people was extraordinarily difficult. Oh, and another thing I picked up from his oral history, he described how he was a bit unhappy with some of the things he was doing with Hubble in his NOVA search. He thought it was not important enough. But it was telling in his biography how he says, I think they already sensed that at the time that I was a little bit of the trouble and I wasn't quite stable enough. Finally, note that of the 3 awards he mentions in his personal biography, 2 were from the very earliest part of his career, within a few years of starting at Palomar. Okay, enough foreshadowing. And I want to step back for a moment here. I don't mean to pass myself off as having thoroughly researched this man and knowing all about him, but I have read a little and I explored a few questions. And I found it curious in what I did read that I seemed to be missing some stuff that I should have seen. Where were the rewards and accolades and continued accomplishments you find with other scientists? What happened to the accolades after those early years? But let's leave that alone. Those early years were back when things were going great for him, and it seemed nobody saw much in that way of his peculiarities early on. He had access to the greatest telescopes on Earth, and because of this, he could collaborate with many people doing very important work. He would go to seminars, international conferences. He'd present his stuff, often on the big stage, and he refers in his books to several places in which big discussions with the big names in astronomy. He was in the in crowd. In his biography and oral history, he speaks of working with Fritz Zwicky, Alan Sandage, Bart Bach, and of course, Edwin Hubble, and a whole lot more astronomers who were the leading theorists and practitioners in the science in the middle of the last century. He did feel, however, that he had been locked out of the hottest new field, quasars. His colleagues had scooped him, and so he went a different direction and devoted himself to looking into new galaxies, how galaxies formed. His hypothesis was that his misshapen peculiar galaxies were galaxies that were just forming. As a result, he spent his time looking into pictures of non-standard galaxies. Now, before we could talk about the pictures of non-standard or peculiar galaxies, we have to know what standard galaxies are. Consider that in the mid-1920s, astronomers did not even know for sure what a galaxy was, or if, besides the Milky Way, they even existed. So by the late 50s and early 60s, when ARP was around, astronomers had come a long way while ARP was trying to take pictures of them. There were various classifications of the morphologies of galaxies. Hubble's tuning fork classification stands out today still, even though most professionals find it has lots of flaws. Hubble classified all of the galaxies into their morphology or their shape. This diagram is roughly divided into two parts, ellipticals and spirals. Hubble gave the ellipticals numbers which describe their ellipticity or their elongation. E0 is almost round and E7 is very elliptical. The spirals were assigned from A to C, which characterizes the compactness of their spiral arms. SA spiral, for examples, are tightly wound, whereas SC spirals are more loosely wound. Also, it's worth noting that the size of the round central regions in these spirals, the so-called bulges, increase in size the more tightly wound the spirals are. Then the spiral galaxies are subdivided into these two groups, normal spirals and barred spirals. In a barred spiral, a spiral runs through the central bulge. And note that in barred spirals, the arms usually start at the end of the bar instead of from the bulges. Barred spirals have a B in the classification of their names. So Hubble acknowledges that not all of the galaxies fit perfectly into this mold. But if those were standard galaxies, then what are these things? Certainly not standard. They don't fit any of the standard morphology described in Hubble's tuning fork. ARP called them peculiar, and thus was born ARP's catalog of peculiar galaxies. ARP was taking pictures at Palomar. He was particularly interested in those galaxies that did not fit the standard tuning fork model. He eventually came up with a list of 338 of them called the ARP catalog of peculiar galaxies. Now, before the end of my program today, I will get back to the catalog itself because it really is a wonderful set of work, and every amateur astronomer should be familiar with the catalog. And being somewhat wonderful, I'm going to end the program with that. After all, it's best to end the program with something nice, after all the foreshadowing of peculiar things that I have done. Remember all that foreshadowing I did earlier about how Halton and ARP could not get along and how after those first few years of glory and a few awards, he didn't have a lot of friends? Well, we're going to explore those dark caverns of rejection. We're going to explore what he did with his peculiarities. To test the stage for that drama, we need 4 scenes: how galaxies are formed, how they get misshapen, how we use redshifts, and the whole puzzle of quasars. We're going to start sometime after what is known as the Big Bang. The idea is that within a few 100 million years, things had cooled off enough to form thin clouds of atoms and eventually molecules. These had mass of some sort, and so could attract other massive objects like themselves. When two of them joined together gravitationally, they had even more mass and could attract even more. They still had motion, however, and so eventually the clumps of mass started floating around the universe. The bigger clumps got bigger and left voids between them and the other masses. Occasionally, the masses coalesced and formed even bigger masses. The whole dance went on for millions of years until some 13 billion years or so we had galaxies scattered throughout the universe. And you saw in the previous slides that galaxies are in motion and they have lots of gravity. So it's possible for them to collide with one another. Our nearest big galaxy, Andromeda, looks like it's just floating peacefully in empty space some 2.5 million light years away. However, it is in fact moving towards the Milky Way at about 60 times freeway speeds, 68 miles a second. Of course, that will speed up as it gets closer, and we will both be stretched, but we are so empty anyway, the stars will just go whizzing past each other in the emptiness of space. It's happened many times before, the past of the Milky Way, and the larger Milky Way just gobbled up the smaller galaxies and added their stars to our own. The Andromeda galaxy is so big, however, that we'll probably just join together into one large elliptical galaxy called Milkdromeda. Not that we'll be here to see it. The solar system will probably survive the collision and merging, but the sun will have boiled over and pretty much killed off whatever life there was on Earth. And we know this happens because we can see the results of it happening to other galaxies in the universe. Here is a NASA production showing how galaxies move in these collisions and form new shapes. It should be noted that these shapes are exactly the peculiar shapes that made it into ARP's collection, and what Hubble could not classify in his pretty little tuning fork model. And these past few slides pretty much explain the paradigm that astronomers used for the formation of galaxies, how galaxies are colliding and forming new weird shapes. And pretty much all the scientists were practicing their normal sciences by making these theories and finding evidence for them. And everybody pretty much agreed, except ARP. One other background scene we need to set is about how astronomers know how galaxies or stars move. We've lately been able to measure positions over time with enough accuracy and enough time to see some actual lateral movement of stars, but not whether the object is moving towards us or away from us. But as many as 100 years ago, we could use the Doppler shift to tell if something is moving towards us or away from us. The Doppler effect is easier to explain with sound. It says that as something is approaching you, the sound waves are compressed. This makes them a higher pitch. An ambulance or a jet plane flying towards you is a higher pitch than one going away from you. The same goes for light waves, except that instead of a higher or lower pitched tone, there are changes in the color of light. As something comes towards us, the light is bluer, and as something goes away from us, it gets redder. And the faster it is moving, the more extreme the color change will be. So all we have to do, one would think, is measure the color of the light, and we can tell how something is moving. Of course, how do we measure the color of the light if we don't know how far away it is or how fast it's moving in the first place? Well, we know that whenever we measure certain things in the lab, at rest with respect to the spectrometer that's measuring it, they are always the same color or colors. Hydrogen alpha always glows in this little bit of off pink. Light can be broken down into its constituent parts, and when you do that, you get light glowing in certain colors. These colors make lines in a spectroscope. Here, for instance, are the lines one would find if we separate the different colors of glowing hydrogen. But When the light source is moving, the lines shift from one level to another. At rest, they may be here, but when they're moving away from us, they shift towards the red. So these black lines you see will be shifting away from us. This shift, however, really becomes important when we notice, as we did in the early decades of the last century, that the further something is away from us, but generally, the faster it is moving away from us. And if everything is generally moving away from us and everything else, then once upon a time, everything must have been in the same place. And we're now living in an expanding universe. The final piece, the final scene of the background that we need to explore is what is happening in the field of quasars. And ARP, just a freshly minted PhD from Caltech, is establishing himself with the biggest telescope in the world. But it is a visible telescope, a visible light telescope that deals with this range of the electromagnetic spectrum. The electromagnetic spectrum has lots of other type of light energy coming towards us. Other astronomers using radio telescopes are finding something called quasars. The quasars were blazing away so energetically that most of their emissions were in this radio range. What visible light they may have had was extremely weak, and it was unrecognizable at first. Other astronomers using radio telescopes are finding something called quasars. The quasars are blazing away so energetically that most of their emissions were in the radio range. What visible light they must have was weak and unrecognizable. But ARP cannot at first see the quasars in his optical telescopes. They don't show well in visible light. So he had these immensely bright radio sources, but no easily seen visible source for them. Poor ARP was using the wrong part of the electromagnetic spectrum to find quasars. The electromagnetic spectrum is much wider than just the visible range and include gamma waves all the way up through the radio waves. So it's a big thing, and he was only looking at one part. And it was the wrong part for the cool things that they were finding. Quasars were bright enough in radio energy, but it took a while to find them in visible energy. Finally, they got some spectroscopy on them, but it did not make sense. The lines were not recognizable until Martin Schmidt, after examining the strange emission lines in the spectra of quasars, suggested that astronomers were seeing normal emission lines that were highly shifted towards the red end of the electromagnetic spectrum. Now, through the 60s and early 70s, the astronomical world was abuzz with these discoveries. There were all sorts of theories about what they were. So far redshifted, they must have been moving away very fast and must have been very old. But what the electromagnetic waves represented was very young when they were transmitted. So the theory developed, they must be what galaxies looked like when the universe was very young. They were baby galaxies screaming out noisily as only newborns could do. It looked like the theorists working together had figured out these new quasar things. A new paradigm had been born. They were the centers of the early galaxies pouring out tremendous radio energy. They were far distant and receding most rapidly. They were clear proof of the Big Bang theory that had come to dominate cosmological thinking. Everybody had come together in a new paradigm of how the world worked. Well, everybody except ARP, who could not see them because he could only had his fancy 200-inch Palomar telescope that could only see things in visible light. All the guys he went to graduate school with, everybody he went to graduate school with, were finding things that he could not see. So everybody is getting fat and happy and making great discoveries. Well, except for Halton and ARP, at least for our story. ARP was using a visible light telescope, and pretty much the exciting discoveries were in radio astronomy. He became a disbeliever in what he could not see. He was a critic of the expanding universe theory. Now, there were others that criticized the theory. The other detractors, most of them were in what was called the steady state school of thought. The steady state model asserts that although the universe is expanding, it nevertheless does not change its appearance from time to time. Those who adhered to the perfect cosmological principle felt the universe had no beginning and no end. This required that matter be continually created in order to keep the universe's density from decreasing. Influential papers on steady state cosmologies were published by Herman Bondi, Thomas Gold, Fred Hoyle in 1948. Similar models had been proposed earlier by William Duncan Macmillan, among others. Fred Hoyle so disliked the idea of a universe that evolved from an infinitesimally small point to the present day that he ridiculed it as a Big Bang, and the name stuck. And because we are amateur astronomers, I should say, we must recognize one of our own, John Dobson. John Dobson was an amateur astronomer, but he was a strong advocate of his own, rather non-academic version of the story of the cosmos. But our Halton, he was the leader of the pack from what I could figure out. He was, at least for our story, the guy that said, nah, that Big Bang thing, that just doesn't work. Now, I got most of the content for the next few slides from two sources: an oral history recorded by Halton Arp in 1975, and a lecture about the redshift controversy by Barbara Becker. I must caution again that I have tried to put together the sequence of events as well as I can, but don't use this in your PhD thesis in the history of astronomy. I gathered that by around 1960, Halton Arp was interested in galactic evolution. That is, how galaxies were formed and evolved. He said later that this interested him because it was the one place in astronomy where you could run experiments. I think he meant by that you could study and classify lots of examples of observed galaxies, and from their commonalities, start to draw causative conclusions. So he decided to spend a lot of time taking pictures of peculiar galaxies. I found a number of origin stories, generally told without dates, to nail down the sequence of events. One story he tells about quasars were first discovered in 1963 or so, but he did not get in on the ground floor. He had made some observations, but even though his work was submitted first, others, particularly Alan Sandage, had theirs published before him. Furthermore, he complained that early on, the information about the location of quasi-stellar radio sources, quasars, had been kept mostly to a select few astronomers, and he was simply not in their circle. So he could not help with that. His early contributions to quasars was limited to trying to help identify optical targets at the locations of reported quasars. In his book, Seeing Red, he tells the story of a radio astronomer asking him for a picture of a certain location. Arp already had a picture at that location since he had researched the area and found a disturbed galaxy there, a peculiar galaxy. And yes, there was a peculiar galaxy right at the location of this particular quasar. But I think this was something late in the Arp against the world story, because Arp used the incident to illustrate the wall of denial that was being built around him by the establishment of professional astronomers. Arp also tells an origin story that appears sometime after he began his images of peculiar galaxies, and he had a collection of them. By now, he apparently had knowledge of just where some of the quasars were. It was a rainy night just south of Temecula on Palomar Mountain, and he could not use his big scope on the top of the hill. So he sat in the Palomar Library and tried to match some of his peculiar galaxies to the radio sources. He found a number of matches. He started to think that quasars were somehow related to the galaxies he was studying, the galaxies that were just being formed, according to him, the galaxies that had peculiar shapes. And this led him to think that these quasars were not evidence of an expanding universe, but instead something else. Now, if Halton Arp were here, he could probably set me straight on a few of these things. I'm just trying to put together disparate anecdotes that I have found in various places. but I think I have the gist of the story right. At any rate, we do have a date for the publication by Caltech of the Atlas of Peculiar Galaxies in 1966. And in there, he mentions he started on it back in 1962 or so. Taking a step back here, while I may not have all the anecdotes in the right time sequence from ARP's oral history, he says that he had decided to assemble the catalog because he was locked out of quasars and set on finding out about the formation of galaxies. But look at this. How many guys of healthy mind would wander the world declaring, thinking, obviously, nobody liked me? Halton Arp said that he statistically showed that quasars are pretty much related to his peculiar galaxies. To oversimplify, where one finds quasars, they also find peculiar galaxies. He had spent some time looking at images of his peculiar galaxies and the database of quasars. He found that statistically, there was a much greater chance of finding a quasar in the same position as one of his peculiars than in the sky at random. So significant, he claimed, quasars were part of his peculiar shaped galaxies. And he claimed his peculiars were galaxies in formation. Therefore, quasars were some phenomenon related to the formation of galaxies, including local ones. They were not just distant early galaxies, as all the cool crowd astronomers claimed. It was Halton Arp's contention that quasars were formed from existing galaxies, and existing galaxies somehow generated new material, calved it, and ejected it. And as the new material was ejected, it left at a high speed, causing an apparent red shift signal. To understand that, let's take a look at this destroyer. What is the redshift signal coming off of this destroyer? Well, let's go back to what we know about the Doppler shift and the redshift. You have this destroyer crossing your path from left to right. And that's not going to generate much of a Doppler shift. No apparent shift there. The helicopter up here is flying away from you, so its return would be redshifted, indicate that it's flying away slowly. But look at this missile. It's rocketing away from you. It's got a very high redshift. What if the high redshift from the missile was being interpreted as the quasar, a completely independent entity from the destroyer galaxy, when in fact it was just a Doppler shift of mass being ejected from the destroyer, okay? In other words, quasars were just indications that mass were leaving another galaxy, probably a galaxy just forming. They were leaving at such a high rate of speed that they appeared to be very far away if you assumed that things were moving faster the further away they were. This was the nut of Halton Arp's explanation for quasars and proof that the redshift analysis from the other cool crowd was bunk. This was the famous redshift controversy. Arp's contention was that redshift was not a reliable way to tell how a given galaxy, quasar, or other object is moving, or how far away it is, because other factors may be misleading you. And if your whole cosmology is based on the redshift, which tell you that everything is moving away from each other, and the faster it is moving, the further away it is, and therefore all this stuff must have been in the same place together some 14 billion years ago before the Big Bang, then there was no Big Bang. The universe is not expanding, and all you cool astronomers who have rejected me are sissy-poo-poos. Halton Arp was on the wrong side of the astronomical establishment, the wrong side of normal science. Halton Arp was peculiar. Now, I've used the term paradigms a couple of times. The word itself is a little trite. It means a model for how something works, and in particular, for our purposes, how science says the university works. But the word paradigm, an anomaly that I've also used, is it wasn't always trite. It became trite thanks to Well, this book right here. Okay, let me take you back to Claremont Men's College with me. Okay, back to Barbie Sue Rodman's history class in the late 60s. It was there that I first read The Structure of Scientific Revolution. The word paradigm and anomaly existed before this book, but this is the book that made them part of our vernacular. Until its publication in 1962, they were not overworn cliche words. Kuhn's book tells the story of how science changes, in particular, telling us about the Copernican revolution. I used his analysis and that of Gustave Le Bon, who wrote a much less famous book some 50 years before about the psychology of revolution, which foreshadowed Kuhn's approach to the revolution in science. They both explained the common patterns. My thesis explained the common patterns of the French mid-1848 Russian and other revolutions, how they started, how they in some way moved from one paradigm to another or didn't. Kuhn says that science runs for long periods of time with pretty nearly everybody agreeing on how things run. This was Ptolemy. He describes how Ptolemy set the standard for the workings of the solar system. And generally, it was quite useful. It did what it was supposed to do. It described how the planets were supposed to move. But in all history, people generally just follow along, doing what needs to be done, showing that science works. This is the normal work of science. It just trudges along, doing what it needs, and everybody agrees with it. For 1,000 years, people could predict the moon and the sun and the planets and find their way using the Ptolemaic science. They all agreed and got along. Except, Kuhn points out, they don't all agree. Every once in a while, there's an anomaly. Somebody points out a problem, an anomaly. These anomalies are something that's out of sorts, something that does not fit the paradigm properly, and they are ignored or minimized or blamed on bad instrumentation, or the paradigm is slightly adjusted, tweaked ever so slightly that it can go on just as normal sciences. You can add permutations around circles around the way the things are circling in the Ptolemaic world. The paradigm, the structure that science has, goes right along. The paradigm was the overarching theory, the model that hung everything together. The paradigm in normal science had a little stumble when Tycho Brahe came along with better measurements. It had a bigger stumble when Copernicus came up with better math, and when Galileo and Newton explained why the better math actually made more sense. And then the paradigm, it just broke. It was a crisis. And when it broke, it could not go on anymore. It was a crisis. Science is broken. There comes a scientific revolution. People propose and test all sorts of new ideas, and they gather new facts. They recognize anomalies as accurate observations, really, and finally come up with a new paradigm, and they test it. And that runs the scientific world for the next few centuries, or in our case, with the Einsteinian revolution, for about a century. And then this is back to normal science, with people just proving again what they already knew. Halton R., in several books of his biography and in his own oral history, describes how he is treated as someone who did not go along with normal science. With Hubble, the paradigm had changed to redshifted galaxies and the Big Bang, and he found himself holding on to the old paradigm, nearly describing himself as Giordano Bruno, being burned at the stake for suggesting that the Earth went around the sun. He was on the wrong side of the history of science. He so much loved his theory and bent his status so hard to fit that when it would not, he had put himself in that crisis. And thus summarized in terms of Thomas S. Kuhn's and the Structure of Scientific Revolution, the peculiarities of Halton R., who characterized himself as getting along with other people was extraordinarily difficult. But hey, he gave us this catalog of extraordinary and peculiar objects. If you want a copy of the original copy, a catalog, you're out of luck. They're sold out, and they were never published in more than a notebook form. You can get a PDF version of it online. or you can buy a modernized, fancified version of it on eBay. I was going to do that and bring it in for you today, but as much as I love you, I don't love you $999.98. I think that's a mistake on eBay. They happen sometimes. Anyway, the targets were first suggested by a Russian professor, Vorontsov Velyaminov, who had compiled a list of 255 oddly shaped galaxy targets from the original survey of the National Geographic Society's Palomar Sky Survey of 1956. Some of these were culled and others were suggested by other astronomers. The 200-inch Hale telescope captured most of the targets on plates, with the 48-incher with its wider field being used for the larger targets. Altogether, there were some 338 images of galaxies, or 338 ARP entities in his catalog. Of course, ARP considered each target a separate galaxy. We know from seeing how galaxies collide and interact that there was more than one galaxy on many of those plates. So there are more than 338 galaxies involved. The preliminary material in the catalog also included the specifics of the imaging, such as the emulsions, filters, imaging conditions, and all that other cool stuff. Now, you remember Hubble's simple tuning fork for describing all the galaxies. Well, it was a lot harder to describe and classify ARP's galaxy. Their morphology was simply not that simple. Let's expand one of these so you can get the idea. ARP 146 to 148 are galaxies with associated rings. 149 to 152 are galaxies with jets. 153 to 160 are those with disturbed and with anterior absorption. And it goes on. ARP acknowledged that the classifications were not absolutely clean, and he had several cross-references throughout, but that was basically his plan. One cool thing about the ARP PDF collection is that you can click on any of these entries and it will immediately take you to the picture of that particular image in the catalog. Now, it should probably be noted that you've already seen many of the ARP objects. 12 of them are Messiers. Another couple of dozen are in the Herschel 400 and a couple of dozen more in the Hickson groups. So knowing that I have all the Messiers and all the Herschel 400, I can tell you I have already seen some 40 of the objects, even before I started out on my latest quest in the Astronomical League ARP program. I should tell you, though, that many of these ARP objects are teensy-weensy, and you need the biggest of knobs to capture visually after a really tough star hop. I have tried a few of the more obscure, and on my first few hours have succeeded on getting only 2 out of the 7 that I've been looking for, that I had looked for. Now, speaking of the Astronomical League program, if you're not familiar with these programs, you should be. Go to their webpage. On it, you will find so many programs, I can't fit them on the screen here. There are some 60 programs to help you sharpen your skills and become a better observer. It's one thing to set a scope up and call over the neighborhood on the next RP spot or something in your next pan and say, hey, what you looking at tonight, Bubba? You know, yeah, you get to see the Andromeda Galaxy, and maybe you're at the right time of the year for M42 to show up for you. But with an Astronomical League observing list, you'll see all of that and more. If you get enough of them done, you get to be called a Master Observer, and you get the Master Observer certificate. I am number 191 on the list of Astronomical League Master Observers. One of my few real long-term accomplishments in life. It doesn't make up for missing out on being an Eagle Scout, but you know, it is something to be proud of. Yes, there is an ARP observing program. It is one of the few you can do with a camera and a go-to scope. You do not have to get all 338, just get 100 of them. But you have to make notes and you have to verify that you got the targets that you sought. It's not one of the easiest programs, but as with any of these programs, I'm sure it'll come with a great sense of achievement once you've got it. You know, as a matter of fact, the Astronomical League has 2 ARP programs because Although I've been talking about the northern ARPs, the one from the original 1966 catalog, there was another effort to find the peculiars in the 1980s for our friends down south. Okay, let's see some pictures. What are the ARP peculiarities really like? To show you that, I'm going to rely on the work of Gary M. of Onalaska, Texas, who one evening, quite some time ago, decided to image all 338 ARP targets. Sometime later, he put them into a collection that he was making of his years of work as an amateur astronomer. He put them into a compendium. And this compendium is a stunning work. Really, the man loves to image. He does quality work. He knows what we need as amateur imagers, and he simply did a fantastic job, not only of imaging, but of putting together a very useful document and an inspiring one, very inspiring, I would say, if I were the gushy kind of guy that says stuff like that. You can get it all of its 38 megabytes glory by going to Cloudy Nights and searching for compendium and taking it from there. Search for compendium in Cloudy Nights. Sorry, there's no way to display the actual URL here since it's about 40 random characters long. It's a download link to a file containing a 420-page ebook with spreadsheets, pictures, links, all sorts of things, technical data on 3,300 unique deep space objects that this man has imaged. I mean, look at this spreadsheet. Want to know what's good to image tonight? Short this spreadsheet out according to the transit date, and you'll see what is the highest on the sky tonight for your session. Really convenient. And then click on the pick and you can see whatever it is that you like. I cannot say enough about it in tribute to this guy, but here we're looking at the pictures of the ARP objects, not to talk about Gary's marvelous achievement. I just used his book as the coolest source I could find for the ARP objects nowadays. So these are the ARP objects. You can see they're very peculiar looking galaxies. That's all 338. Now, I know you didn't have enough time to look at them all, but you can go download the galaxy, the ARP's Atlas of Peculiar Galaxies by just doing a Google search, and you can get that. At any rate, thank you, Halton ARP, for turning us on to all these wonderful peculiarities. I can't say that we agree with you on everything you had to say in your life, Chip, but you sure did find some interesting things to take pictures of. And that, folks, is that. I sure hope you're still there.
Oh, yeah, that was great.
Okay. Are there any questions I might be able to make up answers to? Okay. Perhaps chance alignments and things like that make them look like one peculiar galaxies when in fact they're two galaxies, one of which is eating the other one.
Yeah.
At least that's the theory. Who knows? Maybe he's right. I mean, when you get right down to it, in order to explain the Big Bang Theory, you have to posit things like dark energy, dark matter. Where'd those things come from? They came from trying to fix the paradigm of the expanding universe. And they can't prove it. They can't find the energy. They can't find proof of any of that stuff. They're just constructs that they've made to make the paradigm work. These are anomalies that they're trying to theorize away. So maybe Halton Arp was right,
Yeah.
who knows? But he's not in the mainstream. He's not running normal science now, so we can make fun of him.
Okay.
Yeah, I read